these two capacitor will not allow any current. So if the capacitor does not allow any current, then what will happen? If the capacitor does not allow any current, then as if these two capacitor is not present into the circuit, so they are not functioning as a circuit element because they are not conducting any current. They will not allow any current. So these two capacitors will not allow any current, so they does not take part into the circuit operation, does not allowing any current because of the high impedance. This high impedance appears for the low frequency. If the signal at the input side is very low frequency, then these two capacitor impedance becomes very high. So you can consider these two capacitor as an open circuit. So these two capacitor will not take part into the transistor action. That is the low frequency operation. So for low frequencies, if the frequency omega of the signal, this is the frequency, this signal has a low frequency, then these two capacitor will be open circuited. Then your transistor equivalent circuit only contains resistances and these dependent current sources, and that is the low frequency response of the transistor. The gain expression will be real one. Gain expression will not contain any J part, so it will not be complex. But so this circuit actually, when you consider the high frequency, then what will happen? If you increase the frequency of the input signal, if the frequency of the input signal is, you have applied some signal here at the input side of the transistor, the frequency of the signal is very high. So this is a high frequency signal. You can see that the cycles of the signal are very close apart. So this is a very high frequency signal. If the frequency of the input signal to the transistor is very high, then what happened? This omega is very high. So 1 by omega c will be very low. So the impedance of these two capacitor will be very low. Okay. So impedance of these two capacitor will be very low. So then these two capacitor will conduct healthy amount of current. So now these two, for the high frequency, these two capacitor now take part into the circuit and carry current. So this will carry current for the high frequencies, because if the omega is very high, the impedance of these capacitors becomes low. So if the impedance is low, then it carry a healthy amount of current, good amount of current will pass through the capacitor. So now the capacitors take part into the circuit action. So these two capacitor will conduct current, a large amount of current will flow through the capacitors for the high frequency signal. This is possible for this signal. This current will flow for this signal only, okay, for high frequency. But the current will not flow through the capacitor for low frequency signal. For this signal, the current will not flow because of the high impedance. So these two capacitor for the top signal, low frequency signal, open circuited, but the high frequency signal, these two capacitor, you cannot ignore them. The impedance is low and current will flow. You have to account for these capacitors into the circuit. So this is the difference between the low frequency and high frequency operation of the transistor. So what happens? Transistor has some capacitors into its equivalent circuit. The device PNP structure, the PN junction actually contains some equivalent capacitor. So that is why the transistor actually is frequency sensitive device. Low frequencies operation, transistor, the capacitor will not take part. For the high frequency signal, transistor capacitor will come into play. So the response of the transistor for low frequency and high frequency will be different. So that is why the transistor is a frequency sensitive element. So in this way, you have two types of response of the transistor. One is the low frequency response, another is the high frequency response. In the high frequency response, of the transistor, you have these capacitors. And these capacitors, you know, the impedance is complex, so the gain expression becomes complex for the transistor. Have you got it? Have you understood this one? What do you mean by the low frequency and the high frequency of a particular device? This is applicable for any device. It is not only for the transistor. It is also applicable for the FET, MOSFET, other three-terminal devices. Also applicable this concept. When you switch into the high frequency, when you require a high frequency signal to be amplified, then your transistor equivalent circuit will be different, and the capacitors will come into play into the circuit, equivalent circuit. Have you understood this one? Have you got this one? Are you getting me?
Yes, sir.
Have you understood this one?
Yes, sir.
Everybody? Is there any question? Is there any question for anybody to such that what is the difference between the high frequency and low frequency model response of the transistor? You can find in several books, okay, but you need to understand that why it is called the high frequency, why it is called the low frequency. Okay, then we now uh, we will now actually calculate some parameter that will give you some insight of the transistor, that you can understand the transistor. You can understand the transistor with the help of this equivalent circuit more. So that we are going to do. Now this circuit is a very large circuit. This circuit is a very large circuit. If you apply this circuit instead of a transistor, you replace the transistor by this equivalent circuit, then the analysis will be very complicated. You can see that this circuit is very complicated circuit, very large circuit. You require a computer solution to analyze this entire circuit. Okay, what you need to do that you have to simplify this circuit. We can simplify this circuit little bit, then we can use this circuit in the analysis process. That will be easy. What are the simplification? The simplification is this RB resistance, which is the n-type PNP, n base. The n-type material resistance, RB resistance, is very small, 1 ohm, 2 ohm, very close to 0 ohm. Okay, so this resistance as if it is a short circuit, very low resistance, so you can make this RB resistance as a short circuit. Zero resistance, you can assume that RB is a zero resistance. Similarly, this REX resistance, this resistance also is the n material resistance of the emitter. So this resistance has a value also 1 to 2 ohm. So you can assume that as if there is no resistance, so this resistance is short circuited. So this, again, this resistance you can assume it as a short circuit or zero resistance. And similarly, this RC resistance, the collector material resistance, that is the NPN, N material resistance, this RC resistance is also very small, 1 to 2 ohm. So you can consider that as if it is a zero resistance, so you can short this resistance also. So these three resistances in the circuit, you can assume it as a zero resistance or short circuit. And these resistance are mu. Okay, this R mu resistance is the base, and between the base and emitter, between the base and collector, you have a reverse bias base collector junction, and this R mu resistance is the reverse bias diffusion resistance R mu. And this reverse bias, you know that whenever a PN junction is in the reverse bias, hardly any current flow, only the minority saturation current flow. So that is why this R mu resistance is a very high value. It is of the order of several mega ohm. So this R mu resistance is a very high value. No current actually flows through this R mu resistance because of the high value. So you can discard this one. As if it is an open circuit, as if the resistance of this is so high that you can disconnect the resistance. You can make the open circuit to this resistance. Okay, because the resistance value is close to infinity, so you can open circuit. So you can discard R mu resistance into the equivalent circuit. So these are the simplifications, as well as this capacitance. This capacitance Cs, this capacitance is very low capacitance, substrate capacitance. Between the collector and the substrate, you have a junction, and that actually gives you this capacitance Cs, and this capacitance is also very low value. So the impedance of this capacitor is very high, so you can discard this one also. You can discard this one also. Then if you do this, then your rest of the circuit will be a little bit simpler, and that is called the simplified hybrid equivalent model. If we do all this simplification, that RB, REX, RC is zero resistance, RMU is the infinity resistance or open circuit, and CS is discarded, it is also open circuit, then your complete hybrid equivalent model will be a little bit simpler. And to analyze the circuit will be a little bit simpler, and you can analyze the circuit without the computer. So then what will happen? Then the circuit will be simpler one, and you can see that. So this is the simplified hybrid equivalent model. You can see. So this is the simplified hybrid equivalent model. Here you had a RB resistance that have been discarded, and at the collector also here, in the collector terminal also, in this side, in the collector terminal, you had an resistance that have been discarded, and the emitter side also you had a resistance that also have been discarded. So this resistance also have been discarded. Okay, and also there is a reverse bias diffusion resistance between the B dash and base and collector, and this resistance also have been discarded. It has been open circuited, and there is a substrate capacitor was there, that is also have been discarded. So there was a substrate capacitor here, and that also have been discarded between the ground and the substrate. So these parameters have been discarded, then the circuit have been simplified one. So you will get this simplified circuit. So this is the simplified circuit. This is called the simplified hybrid equivalent model, where the circuit components are less and you can analyze this circuit. It is a simple one. Now we will analyze this circuit and try to understand the transistor behavior, mainly the frequency response. How? We will calculate the short circuit current gain of the transistor. We will calculate this parameter, short circuit current gain of the transistor. How to do that one, the short circuit current gain? What we will do here into this circuit, that this is your input base terminal, this is the base terminal, this is your input of the transistor. Base terminal is the input. Okay, here you apply some signal, so signal will be applied here, and this emitter terminal, so this is your emitter terminal which is grounded. Okay, emitter of the transistor is grounded, and collector of the transistor, this is the collector terminal. So this collector of the transistor is the output terminal of the transistor. Here you will get your amplified signal. So the collector terminal becomes the output terminal, base terminal becomes the input terminal. So here you will get your amplified signal, as it is a common emitter amplifier. So you will get the signal like this. So the signal will be opposite, 180 degree phase shift you will get at the collector terminal. So you will get some amplification like this. Okay, let me remind you, this equivalent circuit only handles the AC. Okay, this equivalent circuit is the AC equivalent circuit. That means it only gets input signal as a AC and gives the output signal as a amplified AC signal. The biasing DC currents or biasing DC is not included here. You have a transistor, you bias it, then the transistor becomes the operating condition. That means the base emitter becomes forward bias and the base collector becomes reverse bias, and the transistor is in the middle of the active region. Then we have extracted this equivalent circuit. Okay, after biasing, that means whenever the transistor is in the active region, that means the base emitter is forward bias, base collector is reverse bias. When the transistor in the operating condition, then we have extracted this equivalent circuit. So it is the AC equivalent circuit. So at the input, of this circuit you have a AC, at the output of this circuit also you have a AC. So this this is the input base terminal, this is the input signal, and that is the output signal. So this, in this the collector, you are going to output signal, and this is the emitter, which is the common to base. That means with respect to this emitter terminal, you are giving the input signal, and with respect to this emitter terminal, you are getting the output signal. And this base emitter collector, in between these three terminal, you have a transistor, or you have the equivalent circuit of the transistor. Now, what we will do, we will output side of the transistor, we will make it short circuit. So you see that this collector terminal is short circuited by this wire to the ground. So this is the ground line. So the output side, that the collector is grounded, that is called the short circuit. So output is short circuited. And at the input side, we are applying an input signal IB at the input side. So this is your input signal. IB is the input signal source we are applying at the base. So in this condition, we try to find the gain of this circuit of the transistor. So when the output is, collector is short circuited, the current flowing through the collector is IC in this way. So this is the current actually flowing in this way. The current is actually flowing in this way. So this is the current actually, collector current flowing at the output side, and in the collector current you have this amplified signal. Though it is a short circuit, but in the collector side you have this amplified signal, and at the input side you have this input signal. Okay, so we will calculate this output current IC by input current IB. That will be the gain of the transistor, and we will calculate this thing from this equivalent circuit. Have you understood this one, what we are going to do? I hope so that you have understood and got this one. So now we have some circuit analysis, because you are familiar with the circuit analysis, that how to analyze this circuit. This is not a very complicated circuit. This is a very simple circuit. Just you have to follow the circuit rules, the circuit theory rules, that will give you the circuit analysis. Will give you that circuit analysis will give you the gain expression. Is this, can you see the figure clearly? Is this dimension is okay?
Yes, sir.
Okay.
Yes, sir.
We will apply KCL equation. This is a circuit. Now it is, forget about the transistor now. You have a equivalent circuit of the transistor, and we have to analyze the circuit. Now it is a circuit theory application. So you have the transistor in the circuit form. It is not in the device form. It is in the circuit form. Input is IB, output is IC, and we have to find the ratio of IC by IB. That will give you the gain of this circuit or gain of the transistor. Now we will apply KCL equation. First, the circuit theory rules, the circuit theory laws, we will apply the KCL equation at the input node. So what we will do, we will apply the KCL equation like this. The KCL equation at this point, input point. Okay, so this is the input point B. Base is the input of the transistor, and this node, base node, is the input of the transistor. We will apply a KCL equation at the base node. So this node, what will be the KCL equation? KCL equation is the summation of algebraic sum of all the currents will be 0, or the inward current should be outward current. So this is the KCL equation. So if you consider this node, then what are the currents actually flowing towards, what will be the KCL equation of this node? Can anybody say? So this node has 3 branches, you see. So this is branch, this here you have a one branch. In this direction also you have another branch, and in this direction you have the other branch. So 3 branches are connected. 3 circuit branches are connected. In this 3 current path is there for this node. Then we have to determine the current flowing through the different branches. The first one is, this branch contains a current flowing towards the B, which is IB. So this is your IB, because the signal generator is connected here. So this is your IB. What will be the current flowing through this branch? So the current will flow in this way, suppose. Then what will be the current flowing through this branch? The current will flow through this branch. The voltage across this branch is V pi. You see that this is the plus terminal of the V pi, and this is the minus terminal of the voltage developed across this resistance. So voltage across the resistance R pi is V pi. Then what is the current flowing through it? It will be V pi by R pi. V pi by R pi. Yes, it is V pi by R pi. So this is the current actually flowing through the second branch. Suppose there is another branch. So this branch. So suppose the current is flowing in this direction. Suppose then you have to calculate this current. Okay, so this another branch is actually there is a current is flowing. Current. Can anybody say what will be that current? This current actually divides into two ways. One flowing through C mu, and one flowing through C mu, another flowing through this C pi. It's not it. This current has a division. It actually goes through C mu one part, another part goes through C pi. So this current has a two division branches. So you have to calculate the current flowing through C mu and C pi. What is the current actually flowing through C pi? What is the voltage across C pi?
V pi.
V pi, yes, very good. It is the voltage across the C pi is V pi, because R pi and C pi are parallel. So this V pi voltage is also the voltage of the capacitor C pi. So what is the current is actually flowing through the C pi? It is your V pi divided by j omega C pi. Is not it?
Yes, sir.
It is j omega and C pi. This is the current actually flowing through the capacitor C pi. And what is the current flowing through the capacitor C mu? You have to find the voltage across the capacitor C mu. So you have to find this voltage, this point and this point voltage. Then you can find the current flowing through the capacitor C mu. What will be that voltage? Can anybody guess?
Sir, by voltage divider rule, we can find this.
How? There is no need to divide the voltage. You see that there is a definite voltage appearing across C mu. You just carefully see the voltages. Okay, you see there here. So this terminal of the capacitor is actually connected to this point. So it is connected to plus terminal of the V pi. It's not it. This plus terminal, it is connected to plus terminal potential of the V pi.
Yes,
and the
sir.
other terminal you see is through the short circuit, because the output is short circuited. So other terminal comes through the short circuit to this ground line to the other end of the V pi potential, this minus. So actually across the C mu you have the plus minus V pi. Is not it? Have you understood this one?
Yes, sir.
As the output is short circuited, this minus actually through this short circuit, it actually comes to the other end. So this side is your plus and this side is minus of the capacitor, and that voltage is your V pi. Okay, then what will be the current flowing through this C mu? It will be V pi divided by 1 by j omega C mu. Is not it? Have you got
Yes,
this
sir.
one? So you see the three branches through the three branches of this capacitor. Through three branches of the capacitor, three branches from the base node. This is the base node. So through this resistance, you have the current V pi by R pi. Through this capacitor, you have the current V pi by j omega C pi, and through this capacitor C mu, you have the current V pi by j omega C mu. That should be equal to the inward current, which is driven by the source IB. So this is the equation at the base node. It's not it? So that is the equation, and we can very easily get this one. So this is the equation. You just see that the equation is written here, the same equation, that the supply current IB should be equal to the current flowing through the resistance R pi, that is V pi by R pi, current flowing through the resistance a capacitance C pi, that is V pi by 1 by j omega C pi, and current flowing through the capacitor C mu, that is V pi by, again V pi by 1 by j omega C mu. So this is the KCL equation at node B. Okay, and so after this equation, we have got the KCL equation at node B, that is input node of the transistor. So this is your KCL equation, and we can simplify this one. This expression, 1 by j omega C pi, 1 by j omega C mu, you can get, and it will go to the numerator side. So ultimately, you will get this one. You take the V pi common. So it will be, from this expression, you will get 1 by R pi. So this one. And this, from this two, the j omega C pi and j omega C mu will go to the numerator. So you take the V pi common, then it will be j omega into C pi plus C mu. So this will be the expressions for IB. Input current, that is the input signal, actually, input signal current IB at the input node, applying the KCL, you will get the base current IB, which is the input signal current, is this expression. Okay. So we are going to calculate the output current divided by the input current. We have got the input current expression. Now we will try to find out the, we will now apply the KCL equation at the output node. So again, we apply the KCL equation at the output node, because we are trying to find the ratio of IC, which is the output current, divided by the input signal current IB, because this ratio will give you the gain of the amplifier or the transistor. Now we apply the KCL equation at the output node, this collector. So this is your output node. So here we will apply some KCL equation here. So if we apply the KCL equation at the collector point, collector node, then how to apply the KCL equation? So this node has three branches again. One branch, one current will flow in this direction through the C mu, another current will flow in this direction, and another current will flow in this direction. So these three current you have to calculate. Can you calculate this one? Can anybody calculate these currents? What is the actually current flowing through C mu? Just similarly, just you have previously we have seen that what is the voltage across the capacitor C mu. What is the voltage across the capacitor C mu?
V pi.
V pi, we have obtained that it is V pi. So the voltage across capacitor C mu is plus minus V pi. Is not it? So if the polarity of the voltage appears to be like this, because you know that this plus is coming here and this minus is coming through this ground path, through the short path to this other end. So this minus is actually coming to the other end of the capacitor. So the voltage across the capacitor is V pi. So what will be the current flowing? Current will actually flow in this direction, because the plus terminal is on the left hand side and the minus terminal on the right hand side. So the current will flow in this direction, and that current, as we have calculated earlier, that will be the same direction current, the same magnitude current will flow, V pi by 1 by j omega C mu. So this is the current, this one. And through this path, this is the current generator is, what is the current actually flowing? That current is Gm by V pi, already given, already calculated. So this is a current source is connected. This is the transistor main action. And this current source has a magnitude Gm V pi. So definitely through that branch, this current will flow. In a electrical circuit, if you have a current source in any branch, no other current can go through the current sources. Only the current source magnitude current will flow through the branch. Why it is so? Because you know that the current source has an infinite input impedance. No other branch, no other external energy source can flow the current through the current sources. So that is why this branch only contains the current which is Gm V pi. Okay. Then the last one, that the through the resistance R0, what will be the current actually flowing? Can anybody say? What will be the current actually flowing through the resistance branch? Through this branch R0?
V pi by R0.
V pi by R0. Is that correct? Is there any other argument is there? Anyone wants to try to? Any other?
Sir, no current flow.
Why?
The resistance shorted, sir.
Yeah, good. You have the earlier answer. You have just a hurried one, but you have tried that R pi, V pi. Your friend has calculated in a wrong way that V pi will not appear across the resistance R0. You just carefully see the earlier who has answered that this V pi cannot appear across this resistance R0 because you carefully see that this point of the resistance and this point of the resistance are short circuited. Have you understood?
Yes,
It's
sir.
not. Yes, you see that. So the this point and this point is short circuited by this path, by this electrical path. So the two end of the resistance potential will be same. So no current will flow through this resistance. So no current will flow through this resistance. Only the current will flow through this capacitor and this current generator, and that will give you the output current. So that will give you the output current. But through this short circuit, you have a current. This is the collector current. This current will flow, but this current will not flow in this direction. This current will not flow in this direction. This current will flow in this direction and in this direction, in the opposite direction. So you have to now apply this current magnitude. So the what will be the KCL equation? The inward current to the collector point. So this is one current V pi by 1 by j omega c mu plus the collector current IC through the short circuit. This two inward current is the outgoing current Gm V pi. This is the KCL equation. This will be the KCL equation for the collector node. So this we can, if you apply this one, then that will be the KCL equation. So KCL equation at the output node, you see the same equation that what we have calculated, that is have been written here. So KCL equation is that through the C mu, you have this current V pi by 1 by j omega C mu. Through the short circuit, you have IC current. The summation of these two currents should be the current generator current Gm V pi. So this is the KCL equation you can get by applying the KCL at the output node. So you see that this current V pi by j omega C mu, this current, which is the inward current IC, should be equal to the summation of these two current IC plus V pi by j omega C mu should be equal to Gm V pi. So that have been done into that KCL equation. That is the KCL equation at the collector node. So that have been done here. So this is the KCL equation. So, okay, I hope that you have understood this KCL equation. So at the output side, we have applied this KCL equation. At the input side, we have applied another KCL equation. So we can now, after some algebra, then we can get our ratio, that what will be the output current by the input current. So now you see, so this from this equation, just sorry, from this equation, we can get this one very easily. Okay. from this equation, because if you only isolate IC, so you have to make this in this side of the equation. So it will be Gm V pi. You take the V pi common. So you take the V pi common. So this is your Gm V pi minus V pi into j omega c mu. So you take the V pi common. So it will be minus j omega c mu. So this is your IC equation, the collector current equation in terms of V pi, input voltage. Okay. This equation appears. This equation actually appears due to the Kcl equation applied to the collector node. Now, from this equation, we extract V pi. From this equation, we extract V pi. It is very simple. That from this equation, we extract V pi. So if we extract V pi from here, so it will be just IC divided by Gm minus j omega c mu. So this is the equation. V pi, and you know that V pi is the base emitter junction voltage, forward bias. Then this V pi expression, what we have obtained from the collector node, this V pi expression we will substitute into the Kcl equation for the base node. Okay, you see that this V pi, from the collector side, we have obtained an expression, this expression. We will substitute this expression into this V pi, which is the Kcl equation at the base node. So we substitute V pi here from this equation. Okay. Then if you substitute this one, so in this position, you have, instead of V pi, you have IC divided by Gm minus j omega c mu. So in the numerator, you will have this expression, 1 by r pi plus j omega c pi plus c mu, divided by, in the denominator you have this expression. Okay, so it will be Gm minus j omega c mu, and IC will be in the numerator side. So that will be, if we replace this, if we substitute this V pi into that equation, so ultimately you will get this one. So you will definitely get this one. This is your IC, and this is the numerator, and this is the denominator. Okay, so that we have got from this expression, because you are substituting V pi, you are actually substituting V pi into this expression, so that you will get, so IC into this one divided by Gm minus j omega c mu. So that we have got. So this is, you see the equation, that it is IC into 1 by r pi into j omega c mu plus c pi divided by Gm minus j omega c mu. So we have actually somehow merged the output Kcl node at collector and the input Kcl node at the base, and obtained this equation. Now this equation, you see that left hand side of this equation, so sorry, little bit enlarged this one. So left hand side of this equation, you have the base current, which is the input current, and the right hand side of this equation, after substituting V pi, you get the collector current, which is the output current, and these are the circuit parameters of the transistor. So what will be the gain now of the transistor? The gain, the small signal current gain. Small signal, why it is called the small signal? Because the signal amplitude at the input is very small, such that the transistor does not distort the signal. In case of power amplifier, you have seen that the power amplifier actually handles the large signal. So that is why you get that the signal will be clipped off in case of power amplifier. So, but in case of small signal amplifier, you have a very small signal that will not distort the signal. So input and output of the transistor will maintain the linear relationship. Okay. So output of the transistor is just a number multiplied by the input, that is the gain. So that is called the linear relationship of the transistor. So that is why this small signal actually appears. So what will be the small signal gain? It will be just simply the output current divided by the input current, IC by IB. And from this, you can calculate the IC by IB, and that is also known as HFE. HF is the small signal gain, and E stands for the common emitter because the emitter is grounded. So this will come out to be IC by IB. If you calculate this one, so this will be come out to be this one from that expression. So you have to put this IB here, and you have to put this whole expression into this side. So that will give you Gm minus j omega c mu by 1 by r pi plus j omega c pi plus c mu. This expression is the gain expression of the transistor. So this actually gives you the desired gain, the designated gain of the transistor. So after extracting the equivalent circuit, you have obtained an gain expression of the transistor from that circuit. What is that gain expression? The gain of the transistor, which is HFE, is this one. Now we will little bit simplify this gain expression to understand the transistor properties. That what are the transistor properties actually hidden into the transistor we actually try to unfold. Now this numerator, see the numerator of this fraction gain expression. This numerator, you see that this j omega c mu, okay, this j omega c mu, this term j omega c mu, the typical value of the high frequency operation, the omega, usually the 500 megahertz, 100 megahertz, this is the value of the frequency. But this capacitor value, the capacitor C mu is very small capacitor. You see that the capacitor value is here, written here. This is the typical value of C mu capacitor of the reverse bias junction capacitor is 0.05 picofarad. Have you heard the picofarad? Picofarad means 10 to the minus 12. So this picofarad actually is your 10 to the power minus 12. So this is a very small capacitor, 10 to the minus 12. Okay, this is your 10 to the minus 12 capacitor. So that means, sorry, it is actually 10 to the minus 12. So 10 to the minus 12, you can understand that how small the capacitor, not only 10 to the minus 12, it is 0.05 into 10 to the minus 12. So this capacitor is a very small capacitor. So this product, j omega into c mu, the frequency you can increase, but you can increase the frequency, but still the capacitor value is so small that this omega c mu will become very small than Gm, because the gain of the transistor Gm this Gm value is 50 milliampere per volt. So this is the order of the Gm value. So you can discard this j omega c mu from the numerator because it is extremely small compared to the Gm. So you can discard that one. There will be no error. Practically, there will be no error if you do this assumption. So we can discard this one. So if you discard this one, then we will get the gain expression like this. So this is your gain expression of the transistor. So HFE nearly equal to, because of that approximation, it has been nearly equal to. So HFE becomes this one. In the numerator, you have the Gm. In the denominator, you have the entire expression, 1 by r pi plus j omega c pi plus c mu. Now, if you rationalize the numerator and the denominator by r pi, so it will become Gm r pi in the numerator, and in the denominator, if you rationalize this with the r pi, then it will be 1 plus j omega r pi will come here into c pi plus c mu. So that will be your gain expression. So this is your final gain expression that HFE ultimately takes this shape. So the gain of the transistor becomes like this: Gm r pi by 1 plus j omega r pi into c pi plus c mu. So this is a very simple circuit application treatment that actually gives you the gain of the transistor like this. So this is the expression for the gain of the transistor. Okay, I hope that you have understood that the gain of the transistor, this expression, how it actually appears. Now, just okay, before going into the detail, just I want to say something about this gain expression. Now you can understand the behavior of the transistor. Now you can understand the behavior of the transistor just looking into the gain expression. So you see that the gain of the transistor HFE has a J part. The interesting point is that the gain is not real. The gain is complex. You have that J part is there. Okay, can you see that one? Are you getting this one? Can you see this one? The gain
Yes, sir.
expression. So the interesting point that the gain of the transistor in general is a complex quantity. So you see that J comes here. Why the J actually coming here into the gain expression? This J actually makes this gain expression complex. So that is why this is not a real quantity. This is a complex quantity. Why this complex J actually coming here? Because of those capacitors. Okay, the junction capacitors, because C pi and C mu, the forward bias base emitter junction capacitance C pi and the reverse bias base collector junction capacitance C mu, these two capacitors is responsible for this J. You know the capacitor impedance is 1 by j omega C pi, 1 by j omega C mu, from where this J actually appears. So because of the structure of the device, structure of the transistor, within the transistor you have capacitors, that is mainly the junction capacitors, and you know that capacitors is a complex circuit element because the impedance of the capacitor is complex. That is why the overall gain of the transistor